Exponential models are pretty useful, but it's not the only model that we can talk about. Let's look at a few related models. In problem 43, we're given an example where we're dealing with a learning curve. You probably heard that term before. Basically, we're saying that we have a new worker starting out with basically no knowledge about the job that he's in, and it's saying that over time he approaches knowing how to produce the correct number of models, or the correct not models, but produce the correct number of units. I guess you could say that, and it's saying that at maximum a worker can produce 30 units, and they're going to follow a model that the number of units that the worker can produce is equal to 30 times 1 minus e to the kt, where t is the number of days on the job. This is not exactly the same model that we had before. We didn't have this 1 minus part in here. But what this is really saying is that the difference between the maximum of 30 and this model is actually following an exponential decay model. So instead of something like starting at some value and going down to 0, we're instead starting at 0 and following the same shape up to some maximum up here. We essentially took this shape here and flipped it upside down. Exactly the same shape. In this particular case, that maximum is 30. It's slowly approaching 30. So technically here, when they're saying that the maximum number is 30, this model never lets us actually get to 30. Though at some point after we're past, say, 29, we might as well just say, well, they can produce 30 units. But that's not too important here. This can be an approximation for the situation anyways. Actually, we'll just leave the graphs as they are. Now, we do need to find out what the k is if we're going to be solving this problem. And that's why they give us some information. They say after 20 days on the job, a worker is producing 19 units in a day. That means that our n should be 19 when the t is equal to 20. What is the value of k for this worker? So we could have different k's for the different workers. For this particular worker, what is this k? We need to solve this exponential function, or exponential equation. Of course, the very first step is to solve for the exponential itself. Solve for the e to the 20 times k. Go ahead and divide by 30. Go ahead and essentially swap the e to the 20k and the 19/30ths. Of course, 1 minus 19 over 30. Go ahead and make 30 minus 19 on the top to give us 11/30ths. We can turn this into a logarithm. So keep in mind what was inside, the 20k, is now outside, and the outside, the 11/30ths, is now the inside of the logarithm. In other words, k is equal to the natural logarithm of 11 over 30, but then divided by 20. And of course, we're going to turn this into a number now. And we get negative 0.05. Next number is actually a 0, so I'll just round it to there. That's our k value. Now, we're not really asking for the k value. We're asking how many days should pass before this worker is producing 25 units per day. We're basically asking, what is n of 25? What value do we get for the function at 25? Or, no, that's not what we're asking. We're asking what time t makes n equal to 25. That's what we're asking. What t gives us a value of 25? It means we go ahead and just set this equal to 25. Of course, our k is no longer just a k, it's now negative 0.05. So we can go ahead and put that in here. And we get a very similar kind of problem. We're just having to solve this again. So we have 1 minus e to the negative 0.05t is equal to 25 over 30. We go ahead and turn this into e to the negative 0.05t is equal to 1 minus 25 over 30, which is 5/30ths. That means that negative 0.05t is equal to the natural logarithm of this. And when we divide by that amount, we have t is equal to negative natural logarithm of 5/30ths over 0.05. And using a calculator, we get a value of 35.8. That's in days. Now, if we want an integer, maybe we'd round that to 36. So that means after 36 days, this worker should be producing 25 units per day. Another commonly used model is the logistics model. What we're doing in the logistics model is kind of fixing a problem with exponential growth. Because exponential growth seems reasonable, at least up to a point. Let's look at population. In population, you can say the more people that exist, the more babies are made, and the population increases. And so it increases exponentially, because more people mean more babies. However, we'll eventually run out of space and resources. So this can't continue indefinitely. So what we need to do is incorporate a limiting factor onto the situation. Basically, if we can't increase past a certain point, then that certain point has to somehow limit our growth. And we'll incorporate that directly into the differential equation. Remember, we started with a differential equation. dy dt, the derivative of our amount, is proportional to the amount that's already there. But we're going to include an extra factor here. That's the difference between some limit and the amount that we have. This is basically saying how much space is there left. So L here is a limiting factor. It actually turns out that this L is actually telling us the absolute maximum number of people that can be there without things just completely collapsing. Now I'm going to solve you I'm going to spare you the details of actually solving this. This is kind of an annoying one to have to solve by hand. If you take differential equations, which I'm not assuming most of you will do because this is business calculus, you're not taking the regular calculus sequence. This is something that can be solved, but it's kind of tricky to do. Turns out the solutions will look like y is equal to L over 1 plus c e to the minus lkt. So that limiting factor ends up being in the exponential, but the exponential ends up being on the bottom of a fraction. The constant c here can be whatever number we want. It will depend on certain factors. Unlike our exponential growth model, the c here is actually not the initial amount. It's not the initial value. Actually, the initial value here would be L over 1 plus c, and you'd have to solve for the c. But we're not going to get too into all that. We're just going to solve one problem. We're going to apply the logistics model to this situation about number of words per minute that you can type. We have a typing class, and the average number of words per minute typed after t weeks of lessons can be modeled by this logistics equation. Not worrying about the differential equation here, just the formula. let's start by... Actually, wait a second here. So, I pulled this particular picture of the of the problem from a different version of the text. Apparently, the wording here is a little bit different on the parts. The numbers here are actually the same thing, and they do want us to find the same kind of things overall. I just have to modify what I have here a little bit. Okay, so the first thing you want us to do is to graph it and estimate the average number of words per minute typed after 10 weeks. So let's go ahead and graph this thing. So remember, our formula looked like... I'm going to change the n and the t into y and x just so that GeoGebra can do it for us. But we have that y is equal to 95 over 1 plus 8.5 e to the negative 0.12x. So we're going to be ignoring anything below the... or we kind of have to ignore things that are outside of the first quadrant, basically. It's also not quite clear what's really happening here. It looks like we just are following an exponential model. And in fact, that's kind of why the logistics model is sometimes not used, and we just use the exponential model. Because it looks like the exponential model at first. But if we zoom out, we notice that eventually it stops growing as fast and actually slows down and eventually levels off. Let me do something like that. There we go. So this is what our problem is doing. It's starting off here at 10. It's actually 10, I guess 10 words per minute. And then over time it starts going exponential, but then eventually you kind of run out of words, or run out of not really words, but you approach your maximum possible speed at typing. Now it was asking us in the problem to estimate how fast you're typing after 10 weeks. So we could say it's somewhere a little bit more than 25. But we can actually get the exact amount by going ahead and just plugging it in. So for part A, all we're really doing is plugging 10 weeks into our formula. We have 95 over 1 plus 8.5 e to the, well, 0.12 is actually times 10 is actually 1.2. Go ahead and plug that into a calculator, because I'm not going to do it by hand, of course. And we get 26.68, and that's words per minute. Which seems to agree with our graph here. 26 is, or almost 27 is actually kind of reasonable. In part B, this is actually a little bit different. Now we're asking for an example where we know the words per minute, but we don't know the number of weeks. Essentially, when is n of t equal to 70? We can go ahead and look at our graph to kind of estimate that, like we did on the last one. If we look at y equals 70, we have this point here, which looks like it could be maybe 25 weeks, around there. Of course, we can solve for it directly. We just have our formula here, 95 over 1 plus 8.5 e to the negative 0.12 t is equal to 70. I'll divide by 95 and then flip everything upside down. So 1 plus 8.5 e to the negative 0.12 t is equal to 95 over 70. We subtract 1 from both sides and divide by 8.5. I'll have the e to the negative 0.12 t is equal to, well, 95 over 70 minus 1 is actually 25 over 70. But then I'm dividing that by 8.5. And I'm not going to work this out right away. To be a little bit more exact when I put this into a calculator, I want to go ahead and just write out a formula and then do it all at once. That way the calculator can save more digits as I go. Of course, now we turn this into a logarithm. What was inside the exponential is now outside, and the outside is now inside. And finally, I divide by negative 0.12. And plug all this into a calculator. I get an answer of 26.4, and that's in weeks. So 25 was pretty close, but it's actually a little bit more than that. It's 26 and a little bit more weeks. Part C. Does the number of words per minute have a limit as t increases without bound? Basically, can this continue increasing infinitely? Now, if we look at our graph, it looks like probably not. It looks like it's kind of leveling off here. But how do we know that for sure? How do we know it actually does completely level off? Well, notice what happens to our function as we go. This 8.5, well, that's not too relevant, but the e to the minus stuff here, this part is going to 0. So as t goes to infinity, e to the negative 0.12t is going to, shouldn't say equals, is going to 0. Remember, the exponential function approaches a horizontal asymptote of 0 as what's in it goes to negative infinity. And that's what's happening when t is going to infinity. This negative means that we're going to negative infinity in the exponent, and e to that is going to 0. That means that this term in the bottom is just going to go to 0, and so n is just going to go to 95 over 1 plus 0, which is just 95. So the number up on top of the logistics model, remember in our general formula, that was just L. That was our limiting factor. And that's saying that as we let our time go off to infinity, we are going to approach that limiting factor. So when we just put in y equals 95, we're going to be approaching that 95 and actually get pretty close to it. This never actually exceeds that. I mean, if we zoom in, we can tell that it doesn't actually ever equal it. But we do get really, really close. We approach that limiting factor as we go. So, definitely a more complicated model than exponential growth is, but exponential growth can give you wildly inaccurate problems once you get close to those limiting factors. As long as you're not anywhere close to the limit, it's a decent enough model. But if you get onto the order of magnitudes that you need to get to that limiting factor, then you have to start taking that into account. But overall, it's still not too terrible of a model. It doesn't have anything other than an exponential and then a fraction. But that's all we're really going to talk about other models. Really, you don't have to be too concerned with anything other than the exponential growth and decay. That's really the only thing I'm really going to test you on or anything like that. And really, this is just more of an applications of the exponential than anything else. So, we're going to go ahead and leave this here. We do have our exam next week, so make sure you've signed up for that and all that. And I'll see you guys at the exam.